right, let's go ahead and get started on today's awesome lecture. Today I'm going to be working on the last little bit of chapter 1, 1.9, 1.10, a couple of word problems here. And I also promised to help you out with the word problem. We'll do some kind of an active learning aspect in terms of that last word problem on the homework set that's due today. So I thought we would do that in class just to kind of help you guys out with that one. So maybe do some kind of group work or something or other. And I'm also going to be talking about the one problem that seems to be throwing people fits, and that is, how do you show you have a linear transformation, or more importantly, like most of them, how do you show you don't have a linear transformation? So I'll take a look at those two problems in terms of that homework set and stuff. And so, so let's go ahead and get started on today's lecture. So, put my lamp on here, and let's get going. So, the last couple of theorems, and then we'll work on some word problems here. This was from section 1.9. We're looking at the idea of a linear transformation, and we're talking about the two words that we talked about last time, which is one-to-one, injective, and the other word is on-to, which is called surjective. And we talked about the definition last time. But how do I tell if a particular linear transformation is going to be one-to-one or onto? Here's the theorem. It says let T go from Rn to Rm is a linear transformation, and let A be the standard matrix for T. So if you're going from Rn to Rm, any linear transformation can be written as a matrix, and the size of that matrix is going to be M by N, how the system set up with your classic mapping. Okay? Part A says this. T maps Rn onto Rm, so we're going to be onto Rm, if and only if the columns of A span Rm. Now, let's go back to more definitions, warned you about an introduction to class. What does it mean to the word span? To be able to span, that means any vector inside of Rm can be written as a linear combination of, in this case, the columns of A. That's what it means to be inside the span. And so you're talking about the columns of A to be in the span. How many vectors do you have to be in the span? Well, if you got Rm, there are M components, so you're going to have at least M vectors on this guy. And, continuing on, T is one-to-one, injective, if and only if the columns of A are linearly independent. So the idea of spanning means that any vector inside of Rm can be written as a linear combination of the vectors that are the column vectors here. And to be linearly independent means that if I do C1 times your first column plus C2 times the second column plus dot, 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 plus Cm times the third column, and I set it equal to 0, the only solution has to be C1 equals 0, C2 equals 0, C3 equals 0. Okay? So here's that idea of on-to and one-to-one. One-to-one, the columns of A are going to be linearly independent. On-to Rm, the columns of A are going to span all of Rm. Okay? So, meanings and results. So, on-to, surjective. The columns of A span Rm, and let's go a little deeper in that, if and only if the number of columns of A is M or more. Okay? So in terms of this onto, columns A is M or more. I mean, this is kind of the generic possibilities. You'll see where I'm going with this in just a second. And one-to-one, the columns of A are linearly independent if and only if the columns of A is M vectors or less. Okay, this is just a general statement about these guys. It doesn't mean, well, if I got M or more, it's automatically going to span Rm. No, but to be able to span Rm, you got to have at least M or more vectors, is what we're telling you. Is M or more, and to be able to be one-to-one linearly independent, you gotta have M or less. If you got more than M, it's gonna be linearly dependent, is what we're telling you. So there's this relationship here that we want to try to get across here. So, if the columns of A have a chance of being basically, the linear transformation is gonna be onto. If it has a chance of being onto, the columns of A have to span Rm, and the only way that's gonna happen is you've gotta have M or more columns. Okay, and even then, I gotta double check to make sure I don't have a bunch of free variables on that when I start row reduction, but you've gotta have, at least M columns. But to be one-to-one, for the linear transformation to be one-to-one, the columns of A have to be linearly independent. And you can only get linearly independent means that I can't have any free variables on this thing, so the number of columns has to be M or less. If you got more than M, you're automatically gonna get dependent. You got way too many vectors in what you're playing with. And now, note, here at the end, here it says, when a linear transformation is both one-to-one and onto, then the standard matrix for T has gotta be a square matrix. Because the only way you can actually do that is you gotta have more than M, and you gotta have less than M to be onto and one-to-one. What does that make the size matrix gonna be? It's gonna be M, and to be one-to-one and onto here, it's gonna have to be a square matrix. It's gonna be an M by M style matrix. Okay? So, what are we referring to? All right, let me show you. Look at my directions, and here's the beauty of this directions. We're trying to look at these guys without actually having to do all that beautiful math of row reduction and figuring out how many pivots, their linearly independence, and all this other good stuff here. I want to look at the size of the matrix, and I can tell you something about the linear transformation that has been induced by this particular matrix. So the directions say this, okay? Suppose T takes vector x, and it's equal to matrix A times x. So A is the matrix that represents the linear transformation T, which A matrix will give us possibly the possibility of one-to-one or onto. I say it's possibility. I've actually got to do the row reduction, see how many pivots I have and all this other stuff, if I want to know exactly what it's going to do, but I'm not after that. I want the keyword here is the word possibility. I want to look at this size matrix even before I start and go, that sucker is definitely not going to be onto, this guy's definitely not going to be one-to-one, or this guy's definitely going to be one-to-one, or has a chance of being one-to-one. It's one of those things. It's giving me ideas here. So, now, take a look at this particular matrix right here. A, let me write this. A, when is the transformation not one-to-one or not onto just by looking at it? That's what I'm after. I want to be able to look at the matrix and just look at the size of it, and I can tell you something about what's going on in this particular matrix. All right, first off, here we go. I got a matrix right here. I got 2, 1, -1, 0, 5, 3. It is, I went ahead and wrote it down for you, it is 3 by 2. Okay? That tells me right there that T is going to be a linear transformation from R who to R who? From R where? R2 to R3. R3. Does that make sense? Because it's 3 by 2, so that's going to take vectors from R2 and go to R3. What can you tell me about this matrix? Okay? Look at the columns. We're going to R3. How many column vectors do I have? Just look at it. It's 3 by 2. I got 2 of them. Okay? Now, if I'm going to be onto, let me go back and write it up here again so you guys can tell what. If T is going to be, T maps Rn onto Rm, if and only if the columns of A span Rm. So back down here, to be onto, the columns of A span Rm if and only if the number of columns is M or more. M is 3. How many columns we got? 2. What does that mean? That means just by looking at it, I'm going to R3, but because I have 2 columns, this guy is quote unquote not onto. that is the answer I'm after. I can look at it and tell you what's going on without actually, did you see me row reduce anybody to see who's linearly independent? No, I'm looking at the size of it, and I can tell you something about how this matrix represents a linear transformation, and based upon the size of the matrix, whether it even has a possibility of being onto or one-to-one, surjective or injective, using our big words there. Does that make sense? Look at the next one. Here's a matrix right here. What's the size of it? 3 by 4. 3 rows, 4 columns. This tells me I'm going to have a linear transformation going from R who to R who. From R what? It's a 3 by 4 matrix. If this is the matrix A that represents this linear transformation, what vector do I need to multiply it by to be able to multiply a 3 by 4 vector? It's got to be an R4, and where's it going to go? To R3. Catch the pattern. We had a 3 by 2. That took R2 to R3. This one's a 3 by 4, so it's going to take vectors from R4 to R3. Does that make sense? So what can you tell me? Well, first off, how many column vectors do I have? Just looking at it. It says 3 by 4, so I have 4 column vectors, right? Does that make sense? All right. Now, what can you tell me? Well, this thing is 3 by 4, okay? And so we're talking about being, going over here to R3. So again, looking at my descriptions. To be onto, if I have a possibility of being onto, the columns of A span RM if and only if the number of columns is M or more. M is 3. How many do we have? 4. So this guy has a chance of being onto. Does that make sense? To be one-to-one, the columns of A have to be linearly independent, and that's if and only if the number of columns is M or less. M, again, is 3. We're talking about R3 over here. How many columns do I have? 4. So what is this telling me? This guy is definitely not one-to-one. Again, that's the old injective word there, versus this is the surjective word, getting used to our terminology. Does that make sense? Again, don't think this too deep. We're trying to talk about RM. RM is where we're going. So I always set this thing up, and then I compare the number of column vectors. Since I have 4 column vectors, and we're going to R3, I have more vectors than R3. That's okay with onto, but that's really bad with one-to-one. This thing's not one-to-one. This problem right here, I'm going to R3, but I only had 2 column vectors. I had less than the M column vectors, so it possibly could be a one-to-one, but it's definitely not going to be onto by my description. Does that make sense? Take a look at C. This particular matrix is a 2 by 2, negative 1, 1, 0, 2. It is going to take R who to R who? R2 to R2, this representing it. And I happen to have 2 columns, which matches to the R2, the second R2. This is what we're talking about, the RM thing here. So this guy here has the possibility of being what? It is possible to be what? One-to-one and onto. Does that make sense? Because I've got 2 columns and I'm going to R2. M equals 2 and I got 2 columns. And remember, what I mentioned up here was that when a linear transformation is both one-to-one and onto, then the standard matrix is going to be square, and it's going to be that M number. It's going to be M by M. This was M was R2, it's 2 by 2. So this is possible. I would actually have to do the row reduction to show you it really does work. But just looking at the size of the matrix, I can tell you, this has the potential to be 1-to-1 and onto. Does that make sense? Look at the next one. I have a matrix representing a linear transformation. This matrix is 2, 5, -1, -1, -3, 0. It is 2 by 3. So if it is a linear transformation, the T is going to go from R who to R who? R3 to R2. Who is my M? R2. 2 is the M. You got it. How many column vectors do I have? Column vectors, just by looking at it, column vectors is how many? 3. 3 is strictly bigger than 2. This is that M number you're talking about. So can you tell me what's going on this one? It's, okay, it's possibly on 2, but definitely what? Not 1-to-1, that's what I'm after. Not 1-to-1. Definitely not 1-to-1. Does that make sense? And again, what's my reasoning at? Look, I've got 3 column vectors, and I'm going to R2. For 1-to-1, the column vectors have to be linearly independent if and only if the number of columns is M or less. We got more than M. M is 2. I got more than 2 column vectors, so that tells me it's not going to be 1-to-1. Does that make sense? Look at the relationship of not 1-to-1 versus the not onto. Does that make sense? Again, don't think overly dramatic about this. We're talking about the word possibility. If you want to show that it's exactly this, then you got to show that you got a linearly independent, so you got to do your row reduction, check out those pivots, solve for them, and see that all the little coefficients are going to be 0, the only trivial solution. Or if I'm going to be able to span Rm, I should be able to take any vector in Rm, and that's a linear combination of the set of vectors that I have. Okay? So again, this is a nice little theorem to be able to allow us to look at a matrix that represents a linear transformation. And I can tell you pretty much quickly, this has the potential to be 1-to-1 and onto. This definitely is not going to be onto. This definitely is not going to be 1-to-1. That's what we're after with this stuff, just by looking at the size of the matrix. Okay? All right. Got another question for you. So I'm doing certain examples here. Show that T being a linear transformation going from R2 to R3 is 1-to-1. Okay, so I'm talking about proving again. How do I prove this thing is 1-to-1? Okay? Okay, to be able to prove 1-to-1, let me go back to my little papers I just had up here. To be able to prove 1-to-1, 1-to-1 means the columns of A have to be linearly independent. Okay? Linearly independent. So I need to show that columns of A are going to be linearly independent. Here's my problem. This is what I was after here. Look at how I wrote the linear transformation. I didn't write it as a matrix. No, sometimes you're going to have to write it as a matrix. That's my point. So T is going from R2 to R3. You should be able to figure that out. Input, output. R2, look at the vector that you're putting inside of T. X1, X2. That's a 2-component vector. That's coming from R2. What kind of resultant do we get back? What vector do we get back? We get 2 times X1 minus X2, comma, X1, it's a comma in there someplace, and then X1 plus 5X2. Does that make sense? How many components are in this resultant vector? 1, 2, 3 components. Does that make sense? So this is going from R2 to R3. You understand how you're basically playing around with these vectors and figure out, where you're going from and to. So my question is, can you write this guy as a matrix? Because all the stuff we've been playing with is making it look like a matrix representation of that linear transformation here. So, yes.
Is the first one the 2x1, is that like a comma that makes it a
That's a 2x1, that's a 1 right there, minus x2, that's a comma. Then you're going to do x1, that's a comma. And then you got your third component, x1 plus 5 times x2.
So there's 3 of them.
That, R3. There's gotta be 3 components, right? So, how do I write this guy here? Well, maybe, because I'm writing these guys as kind of row vectors, why don't you write them as column vectors? So this would be T of, I'll call them X bar. So you may write them as T of the vector X1, X2. If you want to write this guy as a column, that's fine, but then write this as a column. What would this row vector look like as a column vector? Well, the first component is going to be the first one. That'll be 2x1 minus x2. What's the second component? x1. What is the third component? x1 plus 5x2. Now, what I'm trying to show you in this particular example is I can write vectors as row vectors, or I can write them as column vectors. Now, we've been beating up column vectors, but the problem is when I'm typing up my test, that takes up a lot of space to write a column vector, and I gotta have a special math type stuff on my computer to be able to write that stuff up. I can write row vectors real easy. That's on my keyboard. I can do this kind of stuff. Subscript's a pain, but I got buttons for that. Commas, it's no problem here. Writing them like this, that's a pain. So you should appreciate when I type this crap up for you guys, writing it like this. But you should have the ability to go backwards and forwards. Now, let's write it as a matrix. So this T of this x1, x2 would be equal to what times that vector x1, x2. Remember, row by column. So the first row, I gotta have a 2x1 minus x2, so that's gonna be a 2, -1. Second row with the columns, gotta give me the second row column here, which is just x1. That's 1 on the x1 and 0 on the x2. And the third row times the x1, x2 is gotta give me x1 plus 5x2. That'll be 1x1 plus 5x2. And you went from writing it like this as a vector to writing it as a matrix times the arbitrary x1, x2 vector. Does that make sense? Did you see how I went from here to here? Now you've got it. Your, quote, linear transformation represented by a matrix, that matrix A is the matrix 2, -1, 1, 0, 1, 5. Does that make sense? Oh yeah, what was the question? Oh yeah, the question is, show that this transformation is 1-to-1. How do you show 1-to-1? And I'll write it down here for you. To show a linear transformation is 1-to-1. And what's the fancy word for 1-to-1? Injective, trying to convert you guys over to big words in terms of major math here, okay? Is 1-to-1, then we must show the columns of matrix A, the matrix that represents the linear transformation, is linearly independent. So I'm trying to tie in all this definition stuff that I talked about 3 sections ago. How do I show something as linearly independent? Well, that means I want to do this. I basically want to do base matrix A times X, and I want to set it equal to 0, and to show, to be linearly independent, I must show that X vector has got to be equal to the 0 vector. This is the idea. Okay? Now again, I'm trying to not keep writing the same stuff over and over again because you're supposed to be learning something here. So how do I show a matrix times a vector equals 0? I want to solve for the vector here. What am I going to do? Augment my matrix. So what I'm going to do here is this. Okay? 2, -1, 1, 0, 1, 5. I'm going to augment it with what I'm setting equal to, which is 0 vector, which would, in this case would be the 0, 0, 0 vector. You with me? So, again, what we're trying to do here is the columns of A have to be linearly independent. What are my columns of A? So the columns of A is 2, 1, 1, and the other column of A is what? -1, 0, 5. And to show they are linearly independent, I'm going to take C1 times 2, 1, 1, add that to C2 times -1, 0, 5, and I'm going to set it equal to the 0, 0, 0. This is how you show and solve for C1, C2, and if they're linearly independent, C1 equals 0 and C2 equals 0. But to be able to show this, what I'm really trying to do is where this guy comes from. Does that make sense? I'm tying stuff together for you guys. How would you solve this? Good time to practice. I'm going to go for RREF. Go for it. What's your first move? I like to have a pivot in that top row, top column. I can either multiply by half, probably want to avoid that, or do what else? Which one you want to swap with? I'm going to do with the second one because I already got a 0 in that position, so that sounds like a great guy here. So I'm going to row swap R1 and R2. You with me? That's going to give me 1, 0, augment 0, 2, -1, 0, and 1, 5, 0. Now, what's my next move? Go for it. All right, I'm trying to look for some room here. So multiply -2 times row 1, add it to row 2, and whatever you add to is what you replace. And while you're at it, how about -1 times row 1 and go ahead and add that one to row 3 and replace row 3 with it to save myself some space. That'll give me 1, 0, augment 0. -2 times 1 is -2 plus 2 is 0. -2 times 0 plus -1 is -1. -2 times 0 plus 0 is still 0. -1 times 1 is -1 plus 1 is 0. -1 times 0 plus 5 is 5. -1 times 0 plus 0 is 0. What's your next move? All right, so you can multiply -1 times row 2. That'll give me 1, 0, augment 0, 0, 1, augment 0, because -1 times 0 is 0, and 0, 5, 0. I got one more move. What's my last move? Sweep down. So I'm going to do -5 times row 2, add it to row 3, replacing row 3, and that's going to give me 1, 0, augment 0, 0, 1, augment 0, 0, 0, 0. -5 times 1 is -5 plus 5 is 0. -5 times 0 plus 0 is 0 on the rest of his terms. What is this telling me right here? 3 dots in a triangular fashion means therefore. Remember, you're really trying to solve for this C1, C2 now. What is C1 equal to? 0. And what is C2 equal to? 0. And when you set vectors, the coefficients out front equal to 0, and the only solution you get is C1 equals 0, C2 equals 0, and if you got more of them, more C's equal to 0, what do you got? Therefore, matrix A is columns of matrix A, better English. Columns of matrix A are linearly independent, which means what? If the columns of A are linearly independent, again, another 3 dots in a triangular fashion means therefore, T going from, what was it, R2 to R3 is 1, 2, 1. That's what you were supposed to prove, and you got it. Does that make sense? Again, using this concept, to be able to prove 1 to 1, you got to show me the columns of A are linearly independent. To show on to, I got to show the span of the columns of A, excuse me, the columns of A span Rn. Okay? So, does that make sense? Did I lose you? And again, I'm trying to tie in some of the stuff we've done before into this new material. We're dealing with linear transformation. Now, section, my paper's in order here. Section 1.10 is just word problems again. And I gave you guys a problem last time, and let me see if I got a copy of it. Right here. Before I look at the one from your homework, I want to look at this guy. All right. Again, at the end of the day, we are trying to use matrices to solve systems of equations. So we're trying to show you guys different avenues of where your systems of equations are going to be very advantageous. Okay? So, all right. First thing I want to do is look at circuits. Why? Because of my engineering students in here, and they just love circuits. So here it is. First thing, you have something that's called Ohm's law. Ohm's law basically says voltage is equal to I, which is current, times R, which is resistance. Voltage is equal to current times resistance. So, we have this circuit set up where the little squiggly lines here with these ohms, those are your resistors, okay? And the little big line, little line is where your batteries or your voltage is actually set up. Well, in terms of current and the way current is going to travel, listen to my words, current is going to travel is from the negative side to the positive side. That's the way current travels. So you go from the short side, which is your negative side, to the large side, which is your bigger side, okay? That's considered the positive current. So, what your goal here is each one of these little circuits, and we've got 4 circuits put together, we want to create an equation out of this guy using Ohm's law. Voltage equals current times resistance. So, let's go for your first block here. All right, what do you got here? All right, so I have a battery right there, and we're moving, look at how I orientated my, my current there. We're going from negative to positive, so this is a positive 40 volts here. So that would be 40. Well, what's it equal to? Well, let's take a look at all the resistance that we happen to have here. I think I may have a couple more. Jacob, could you pass out? There's people keep missing out on the last time I passed these out. Okay, so here we go. Look at this. All right, I got current, I1. This is what we're trying to find. This is my unknown. But we're going across this resistor right here, which is 1 ohm. So I got 1 times I1 plus, we got 1 going across this 7 ohm resistor. So that would be plus 7 I1. And we got I1 going across the 4 resistor. That would be plus 4 I1. Does that make sense? But I got a problem. This particular circuit is linked to these 2 guys here. And so if you look at your orientation, this one is going, you see, going counterclockwise here. This one is going clockwise. So counterclockwise, looking at this and the way that's a positive 4 battery, this resistor, 4 resistors, got current coming in this way, but you got a problem. It also has I4 current coming across it going the other direction. Does that make sense? And it's going the other direction, so that's going to be a minus 4. That's an I4 current that we need to be able to solve for. And I got one more. It's down here, 7. It's going this way, but my other current is coming, again, counterclockwise here. So it's going against the I1, so that's going to be a negative 7 I2. Minus 7, I'll put him right there, I2. Does that make sense? Question?
So I see the arrow is going counterclockwise.
Yeah.
Why is it going counterclockwise when the positive side is?
You go from the negative to the positive.
Right.
Negative to positive makes your flow this way.
Right. So on I4.
Oh,
since
I'll get there in a second. No, let's focus on this one first. Now, I got my terminals switched on another. That's another question. Just wait for me here. All right. Just this guy right now. I'm helping you guys out because you got a project on there, on this, on your homework set here. So let's clean that equation up. See, I can combine all these guys right here. What I got? 1, 7, and 4. How much is that? 11, 12. 12 I1, right? Minus 4, let's do it in order. Minus 7 I2 minus 4 I4 is equal to 40. Does that make sense? I combine these guys, minus, I put them in order, minus 7 I2 minus 4 I4 equals 40. Did I lose you guys anywhere? Let's go to I2. All right? What's going on in I2? Well, first off, what do we have attached I2? Look at my orientation for this guy. We're going from negative to positive. This is my current. That would be a positive 30 volts on this guy. And now, resistance times current. So I've got, let's go this direction. I've got a 2 times an I2 plus I got a 6 times an I2 plus I got a 7 times an I2. So we got all that inside, but I got some stuff basically fighting it. What do I have fighting it? Up here, I've got, since we're going this way, the I1 is now compared to the I2 is going in the opposite direction. So that's going to be a minus 7 I1. Does that make sense? And come over here, what about this guy? This is connected to the I3. And this, the I2 is going up. This one is going down. So it's going across this 6 here. That'll be a minus 6 ohms times I3. So these guys are connected with the other currents are going to resist, if you will. Does that make sense? Now, let's write your equation. Again, I like to put them in order. So going, I see an I1 first. That's a minus 7 I1. And then I got these guys here. 2 plus 6 plus 7 I2s. What is that? 9 plus 15 I2s minus 6 I3. And that's equal to 30. Let me circle these guys, because we'll come back and use them later. Did I lose you guys anywhere so far? I'm getting there. Well, I3 now. Okay. Now, I3, look at the orientation of I3, and again, the current is going from the negative, the small side, to the big side, so that's a positive 20 volts there. Okay? Because the current is going the right way. And now, what do I got? I3 is going to turn across the 3 ohm resistor, the 5 ohm resistor, and the 6 ohm resistor. I'll write it like this from Ohm's law. That would be 3I3 plus 5I3 plus 6I3. You with me? But then, who's fighting it? Going the other direction, I've got the I2 going across that 6, and it's going in the other direction, so it's going to be a minus 6I2. And I got another one up here. The I4 is coming across the 5, but it's going in the opposite direction. The current's going in the opposite direction of which the I3 is. So that's going to be a minus 5I4. Does that make sense? Now let's rewrite the equation, combining like terms and putting them in order. I got an I2, minus 6I2. I got a bunch of I3s. I got a 3, I got a 5, I got a 6. That's 11 plus 3, what's that, 14? Plus 14 I3, minus 5 I4, and that's equal to 20 when I combine my like terms. Does that make sense so far? Have I lost you anywhere? Now I'm going to go to your favorite circuit here. All right. Take a look at I4. Now, I did this guy on purpose, and you can see that kind of drill on top of it. I want you guys to pay attention here. Look at the battery, the way it's set up. It's supposed to, current is supposed to go from the negative side to the positive side. That's how current flows. But I flipped the terminals on the battery. You see this current? It's rotating in a, quote, counterclockwise fashion. But when you come across the battery, it's going from the positive side to the negative side. All the other batteries go from the negative to positive, and that's the way you're supposed to orient. Does that make sense? So what does that mean when I flip my terminals on the battery? A Negative voltage, exactly. This is gonna be a negative 10 volts. Does that make sense? Because I switched, and it's not just because of the 10 over here. It's the way the terminals are compared to the flow of the actual circuit inside that we're focusing on in terms of coming into these equations. The current is flowing counterclockwise, but when you hit the terminal, it goes from the positive to negative. That's when you get to the negative terminal. Yes, negative battery.
Are the circuits and the flow like the same for each? And not like that, like the one on the homework, is it supposed to go from negative to positive?
Always supposed to go from negative to positive, yes. So, but be careful, watch, and you'll see the flow. We'll write the little arrow in there, but watch when the terminals are backwards. It should go from the small side to the big side when you're making your current flows, okay? Because that's what happened, because when I come over here, now let's talk about the current. So on this one, I got I4, I got 4 going across the 4 ohm resistor, 4 I4 plus another 4 I4 plus a 5 I4. But we got this current going from these other sides, and you notice those currents and how we set up our circuits here are flowing in the opposite direction. So this is going to give you a negative 4 I1 going here, and across this guy, you see the I4 is going counterclockwise. This one here is going to be fighting that on the bottom side, so that's going to be a minus 5 I3, okay? So again, writing this as an equation here, always like to put them in order. This is a minus 5 I3 plus, oh no, I forgot my little I1 there, minus 4 I1 minus 5 I3 plus 4 plus 4 plus 5, what is that, 8 plus 5, which is what, 13 I4, but it's equal to what? Negative 10, and the negative 10 comes from the fact is my terminals on my battery have been flipped. Yeah.
So if the flow for I4 was going clockwise, then it would have stayed positive instead of
Yes,
negative?
yes. If I was flowing it this way, it would have stayed positive, right? That would have been a positive 10 on this, and I'm still flowing it this way, so it'll be 4I4 by 5. And then you'll see if I was flowing this way and this guy's flowing this way, you would end up adding that guy instead of subtracting them because they're flowing in the same direction. This one, you look at your 5 ohm resistor right here. On the top circuit, it's flowing counterclockwise, so it's going from left to right, but on the bottom, it's still flowing counterclockwise, but when you look at it, it's going from right to left on the bottom side, so they're fighting each other, and that's where your sign difference is going to be at. This is why these guys are negative instead of being positive. If I flip this guy and make him go this way, then it would have been plus, because they would have helped each other, the current would have backed each other up, and the current would have been more going toward, yeah.
Before you wrote the final thing, is that supposed to be a plus and for I4 negative 5 by 3?
This one, yeah, that was positive, so yes, it's positive. This is, because the flow, this is 4, this is 4, this is 5, and it's all going in the positive direction of the I4. All right, so, now, let's write this as a quote system of equations. So from that first equation, what do we have here? We have 12 I1 minus 7 I2, leave a little space there, minus 4 I3 equals 40. From the second equation, I have a negative 7 I1 plus a 15 I2 minus 6 I3, and I am trying to line these guys up, but that's equal to 30. From the third equation, I got a negative 6 I2, there was no I1, plus 14 I3 minus 5 I4, but that's equal to 20. And then I have my last equation, which is a negative 4 I1 minus 5 I3, there was no I2 there, so I left the space there, plus 13 I4, but that was equal to what? Negative 10. Our goal here is to figure out, to make this current, this circuit valid, what do the currents I1, I2, I3, I4 happen to be. Did I screw something up? Let's see here. No, I got this right here.
No, like I see the I-4, but there you have I-3.
Oh, oh. Yeah, okay, that's me actually not paying attention while I'm down. Thank you. Okay, yes. That's an I-4, because that's clearly an I-4 right there. That needs to go right there. All right, now, what I want to do here is I want to write this guy as a matrix. So writing him as a matrix, I got this. This would be 12, negative 7, 0, negative 4, and we're going to go ahead, it's an equation, augment it with 40, negative 7, 15, negative 6, 0, there's no I4 there, equal to 30, 0, negative 6, 14, negative 5, 20, and then the last one is negative 4, 0, negative 5, 13, negative 10. Does that make sense? Now, on a problem like this, I'm going to give you guys a great benefit, because on some problems, I want to see the reduced row echelon form once you solve this thing. On other problems, because this one's going to have really crappy fractional answers here, choose this guy. Okay, so, matrix, edit. I'm going to edit A here. What size matrix is this guy? Augmented matrix. What size is it? How many rows? Rows first. How many rows? 4. How many columns? 5. 4 by 5. And you type them in row-wise. 12, negative 7, 0, negative 4, 40, negative 7, 15, negative 6, 0, 30, 0, negative 6, 14, negative 5, 20, negative 4, 0, negative 5, 13, negative 10. Does that make sense? Now, I'm going to show you guys some tricks on the old calculator here. I just entered it in the calculator, and I'm fast, which means I make bonehead careless errors. So the next thing I do is I'm going to second quit, clear out, and I'm going to go back to matrix, and A, I'm just going to type up, you have to call it bracket A, that's the matrix A, I'm going to hit enter, and I look at it one more time, just to make sure I didn't lose a sign or something like that, because you screw up one thing, you died on this problem. So I typed it in row-wise, so always check it column-wise. 12, negative 7, 0, negative 4, negative 7, 15, negative 6, 0, 0, negative 6, 14, negative 5, negative 4, 0, negative 5, 13. All I get is over arrow, 40, 30, 20, negative 10. I'm happy with this guy. Second quit, clear, and I'm going to go back to matrix, go over to my math, and the most important button out of all these buttons is the RREF. The reduced row echelon form, then you got to go back to second matrix under names and call up 1 matrix A, and mathematically I hit enter, and it gives me crappy answers. But what does it actually give me? Okay, the answer. Here it is. It is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, augmented with 11.43415565, close enough to leave that. 10.550250, 8.0356632, 5.83961094. What is this telling me? This represents the current I1, I2, I3, and I4 is my unknowns, trying to figure out what the currents are. So I1 would be equal to 11.434, I'm just going to go 3 decimal places on this guy. I2 would be equal to 10.550. I3 would be equal to 8.036, down to 3 decimal places, and I4 would be equal to 5.83, 840 actually, if you round it off to 3 decimal places. Right? Did I lose you guys anywhere on this thing? So, question. Any electrical engineers in here? Should be. All right. What is current measured in? Amperes, amps. Ooh, always on this thing. Maybe we forget about loose knowing sometimes. Here we go. Always gotta have units. Does that make sense? Did I lose you guys anywhere with this stuff? What if I got an answer of I3 being negative 8.036? What would that mean? I3, if it's negative, you actually should reverse the flow. Does that make sense? But this is telling me what my actual currents should be to make this system with the resistance and the batteries hooked up to make the actual solution to this thing work it out. Did I lose you guys anywhere? Okay. Question.
So that means where it was the reverse current, where it was going from positive to negative, that means that it's correct, it needs to be that way.
It needs to be that way if you want the I-4 to go actually in the right direction, yeah. But it's the way I happen to hook up the battery. You know, I could have, and it got a negative answer for I-4, that meant that the current should be actually flowing the other way. Does that make sense? I believe you guys have a problem on your little, homework set there. And, I have the problem, but I have it all worked out for me, and that's kind of bad. So, I want to show you all my answers and stuff. So, let's see here, what did I do with my answers? All righty. Let me see, I can do this. Good. Okay. And all I asked you guys to do on this one was set up the equation. I didn't ask you to solve for it because it's a pain in the butt to get it. But so I just wanted you to set up the system here. All right? So, let's do some group work here. Well, it's just one big group. We'll just work on this thing right here together. All right? How's it going to work? So, there's your current right there, I1. Look at your battery terminal. The flow is going counterclockwise, but the battery set up small on top, big on bottom, negative, positive. So that's a positive 30. Does that make sense? Relative to my current. And I've got 1 I1 plus 2 I1 plus 3 I1. But that I1 down here has, that 1 ohm here has an I2 current that's going to be going in the opposite direction. So you're going to have to subtract 1 I1. Does that make sense? And you set up your equation. I meant 1 I2. 1 I2. This is your I2. So what numbers do you get here? 1 plus 2 plus 3. Was that 6? 6 I1. But this one is on, this is only, I2 is only linked this way in the parallel system here. So minus I2, and that will be equal to 30. Look at your second equation. What do you got? This is the I2 equation. Again, look at my battery from negative to positive in this counterclockwise fashion, so it'll be equal to 20. I've got 4I2 plus 4I2 plus 1I2. I believe that's a 9I2. You with me? But then I've got an I1 up here that's going in the opposite direction of where this flow is on the way it's set up. So that'll be a minus 1 I1. And down here, it's going in the opposite direction. I got a minus 4 I3. Does that make sense? Questions? Then, let's take a look at this equation here. Look at my flow and my battery set up. They're all set up nicely. So that's according to the flow on the I3, that battery is going from negative to positive, so that's equal to 40. And what's equal to 40? I've got a 2 I3, a 1 I3, and a 4 I3. I believe that is like 7 I3. But then I gotta take away, because it's going in the opposite direction, a 4I2, and I have to take away, because it's going in the opposite direction, a 2I1 to get my voltage equation here. Does that make sense? And then I got one more. So, battery terminal is good. I4 is going across it from negative to positive, so that's equal to 10. So 10 is equal to 3I4 plus 2I4 plus 2I4. That's what, 7I4. But then I've got 1 taken away over here because it's going the opposite direction, minus 2I3. So minus 2I3 plus 7I4 is equal to 10. Does that make sense? So, do you have the system equations of this guy? All right. So what do I got here? I4 is going across from negative to positive, so it's going to be a positive 10, so it's equal to 10. I4, what's the resistance? You're going 3I4 plus 2I4 plus 2I4. 2 plus 2 plus 3 is 7. That's 7I4. But you got this I3 going in the opposite direction. This is going to the right, but this is flowing to the left. So that's going to be a minus 2I3. So it's minus 2I3 plus 7I4 is equal to the voltage, which is 10. That's your fourth equation. Does that make sense? All right. So, moving this out of the way so you guys don't see it, could you tell me what you got for your answer? What's the first equation? On your mark, get set, go. Good. 6I1 minus I2 equals 30. Second equation. I want them in order. You want to put these guys always in order. There's an I1 on this thing. Negative I1 plus 9I2 minus 4I3 equals 20. What was your third equation? Negative 4I2 plus 7I3 minus 2I4 equals, and what's your last equation? Negative 2I3 plus 7I4 equals 10. And you want the variables to be in order so it's easy to block them off, and then you can go for your matrix and solve the system of equations to be able to figure out what's going on. But I didn't ask you to do that on this homework. I meant to ask you to set it up. All right? Questions? All right? Well, there's one more on that homework set that you guys wanted me to look at. There's some other problems from section 5.10, but the circuits are the most interesting. The rest of them are actually very similar to the problems that I've done before. And it's, but so I'm not going to really focus on many of those other word problems because you got protein, hybrid carbohydrates, and fats, and basically from different non-fat milk, soy, and wheat. Look at those examples in the book. They're very good examples, but they're very straightforward when they set up the chart and how to come up with a matrix and stuff like that. So if I do something like that, I'll give you the chart which actually represents the matrix. So the last thing that I want to talk about here is linear transformations. And I believe it was, what questions was it? It was what? Numbers 10, what numbers was it again? 16 through 21. I'll sit there and look at my numbers again, all right? Yeah, let me do this real quick, so it'll be easier for me to look at.